Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. Today we're going to delve into one of the great mysteries and conundrums underlying the calculus. And it has to do with a very simple object, a circle. So it turns out that understanding the area of a circle is not only subtle, but actually logically problematic. And it's bedeviled people for literally thousands of years. And so we want to talk a little bit about the historical background to this problem. And we'll see that Archimedes figures very prominently, just as he did for the parabola area computation. But I warn you that there is a big divergence here, especially at this point, between this course and pretty well any other course in calculus. And the reason is because we're treating this topic with the delicacy and the, say, skepticism that it really deserves. This is a hugely problematic issue and we cannot skirt around that fact. Okay, so for at least 5,000 years, people have been struggling with the mystery of the circle and this determination of the area of a circle. Say the area of a circle of radius 1. So this is a question. What is the area of a circle of radius 1? Here's a circle, there's a center, there's a radius. We can assume we have some normalization. Got a ruler, that's 1 there. And we want to know how many squares of size 1 fit inside there. Well, people give this area a name. It's of course the Greek letter pi, so this represents the area. But the fact that we have area in quotes here is already alerting us to a potential problem, namely the difficulty in defining this in the first place. So in this course, we're going to give the following highly non-standard answer to this question. Okay, highly non-standard, but logically very good approach. My answer is that there is no precise notion of the area of a circle. That notion is not a precise mathematical notion. Approximately, yes, no problem. Approximately, we can talk about an approximate area. But as for defining a precise area, I claim that that is not only difficult, it's actually impossible. It's something that will forever elude us. It's a goal that we can never attain. Even the definition. This is the crucial thing. It's not the computation, it's the definition of what this concept is. So when it comes to area, the circle, and we'll also see the hyperbola, are very different from a parabola. We get this fundamental divide right at the heart of calculus that students really need to be very familiar with. They need to understand that there's this big separation between what happens in the parabolic case and what happens in the circle or hyperbola case. So even from very early times, people have somehow been aware that this question of the area of a circle is something that's very hard to get one's hands on precisely. That there always seems to be some aspect of ambiguity or approximation involved. And this is a common theme throughout the history of mathematics. This exact problem, the determination of the area of a circle, even of radius 1. And we can go back to the old Babylonian period at least, around 1900 to 1600 BCE, that's the old Babylonian period, and they had a formula for the approximate area of a circle, but it wasn't in terms of a radius. So they didn't think in terms of a circle having necessarily a radius. They thought rather in terms of a circumference. Like if you have a well, then you could perhaps measure around the well more easily than you could from the outside to a supposed sort of imaginary point in the center. So there's some practical reasons why circumference might be easier to deal with than a radius. And in terms of the circumference c, their estimation was that the area of the circle was c squared over 12. It's a little exercise to show you that that's basically equivalent to having pi have a value of 3. In the contemporary Egyptian culture, We have the Ahmes or rind papyrus, one of our famous, one of only a select few records of how the ancient Egyptians thought about mathematics. And this was created around 1650 BC, but it's very clear from the inscription that's actually a copy of earlier work that goes back a few hundred years earlier. And Ahmes refers to the scribe who actually made the copying. And this is problem 48 in that, no, it's actually problem 50 in the papyrus. It's a circular field has diameter 9 ket. What is its area? So here we have a circular field. In this case, the diameter is 9. So we can imagine it being in, say, a square box, and there is 9 in both directions. So here's the solution that's presented in the papyrus. Take away, you, 1/9 of it, namely 1. The remainder is 8. Make you the multiplication, 8 times 8. Becomes it 64, the amount of it. This is, in area, 64 setat. Setat being a unit of area. What they're saying is that if the diameter is 9, you remove 1/9, you get 8. You square the 8, you get an area of 64. So there's a formula here, which is not stated, but this is the formula, that the area is what you get when you start with the d and you subtract 1/9 of d, you square it. That's then 64 over 81 d squared. And implicitly, this is using a value of pi, which is, as you can check, 256 over 81, which turns out to be 4/3 to the 4th. And that's approximately 3.16049. So that's not too bad an approximation to pi, which is usually 3.14159, etc. So that's quite an impressive, very early estimation of pi, okay? So we're putting pi in quotes because from our point of view, pi is not part of our landscape, at least not as a number. We may think about it later on as some kind of approximate interval, which may grow or shrink depending on the circumstances. So there may be a more subtle interpretation of what pi is. But the idea of pi as being an exact number that you can put your finger on, forget it. That's not going to be part of our story. Just not part of our story. But nevertheless, we'll make touch with the historical basis. So whenever we're talking about pi, we should have quotes around it. So imagine quotes around all these formulas pretty well. Okay, now another famous thing that happens is in Euclid, the book 12 actually of the elements. There's 13 books altogether, so this is rather late in the piece. Proposition 2 talks about areas of circles and establishes another important ingredient in our understanding of circles. Euclid says, circles are to another as the squares on the diameters. Here is a circle. Here is a square on the diameter. Okay, so the diameter is that, and this is a square on the diameter. So move the diameter over there, then the square nicely contains the circle. Here's another circle, and a square on its diameter. What's this proposition saying? It's saying that the area of these two circles, their relation, their proportion, is the same as the corresponding relation or proportion between the enclosing squares. Now notice that this is framed in a geometrical language. He's not really saying take the diameter of this circle, measure the diameter, take that number and square it. That's how we would interpret it, and that's how often a modern text would rephrase this in modern language. But what he's saying is actually something different. He's saying take the diameter as a segment. There's a segment. Create a square on that segment. So you create that object. Similarly over here, you create that object. Then the ratio between these two square objects is the same as the ratio between the two circular objects. So in our modern point of view, with modern language, we would say that this is expressing the quadratic dependence of area on the radius, even though the radius doesn't really figure in Euclid's story. So, but we would write area equals pi r squared, telling us that not only is the area of a circle of unit 1 equal to pi, but furthermore, that same constant pi is involved in the area for an arbitrary circle of arbitrary radius r. So that's the quadratic dependence of the area on the radius. But you have to admit it's not a very precise restatement of Euclid. Euclid is getting at something slightly different. It's a different cultural approach to what's really happening here. And now we come to the great Archimedes, who, just as in the parabola case, established really the benchmark computation for the circle. And this really is the benchmark computation. It basically set the tone for circle area investigations for the next close to 2,000 years. So he wrote a treatise called Measurement of a Circle. These are his dates, 287 to 212 BC. And in this work, there's a subtle but important shift that takes place that we should make sure that we are aware of. Okay, there's a shift from areas to arc lengths. So here's a circle, and there's a radius r, and there's a circumference c. It also has an area. So we've seen the formula pi r squared for the area. But there's this other formula for the circumference. Circumference c is 2 pi r. So this is about areas, and this is about arc length. It's about the length, supposedly, of the boundary of the circle. Now, from our point of view of calculus, area is more fundamental than arc length. This is a more fundamental direction of a formula. And so Archimedes, he's really aiming at this formula. He's aiming at calculating the circumference of a circle, say of radius 1. And if he does that, then he also establishes pi. So he can establish pi through this formula rather than through this formula. Now, there's a question as to whether these two pi's are really the same or not. Okay, so there's a theorem to be proven here that the constant of proportionality here and the constant of proportionality here are in fact exactly the same. That's actually a very subtle business that is finessed by almost all treatments of modern mathematics. It's a hugely delicate issue that really requires a very careful setup of Euclidean geometry to get it right and to be able to even do this. But from our point of view, it's not even possible to do this correctly because the pi's themselves represent quantities that we're not able to obtain. Okay, so what I want to alert you to this dichotomy between areas and arc lengths. So nevertheless, Archimedes was interested in the arc length and trying to compute that and trying to estimate pi by a calculation of the circumference. And his strategy was the following. He says, let's start with a regular hexagon of side length 1, which is the same as the radius of our circle. So here's a circle of radius 1, and here's a hexagon. Now this hexagon is made of 6 equilateral triangles. That's an equilateral triangle. There's 6 of them altogether. And so if that side's 1, then that side is 1 as well. So each of these sides here is 1. So a crude estimate for the circumference of this circle is 6 times 1, because that's the circumference of this inscribed hexagon. That will be an underestimate, right? The actual circumference we should expect to be bigger than 6. Okay, so his strategy then is to do the following. And then we're going to replace the hexagon with a 12-sided figure. And we're going to do that by bisecting any one of these segments. So this thing here, we take a perpendicular to that other side. So in other words, we're bisecting that angle, if you like, and obtaining another point on the boundary, which is equidistant from the two that we already have. And then if we join these with line segments, then we get a 12-gon, a regular 12-gon if we do the same thing all the way around. And then he's able to make a calculation. He's able to compute what this length is. Now for us, lengths are problematic, but let's carry on with what Archimedes was thinking. So in his language, he is able to calculate the length of this thing as being the square root of 2 minus the square root of 3. That's a little bit subtle. And so using that, he's able to estimate the new circumference, namely the circumference of the 12gon, as being simply 12 times this. And since he's able to calculate square roots of 3, and then once he gets that, he can plug that into there, and then he can calculate the square root of that thing, then multiply by 12, then he has a new estimate for 2 times pi. And then what he does is he carries on this way. So he knows how to go from one step to another. So at the next step, he subdivides each of the given sides into 2. So he would split that into 2, creating a new point halfway in there, and then he would have a 24-gon, and then a 48-gon, and then by the time he gets up to a 96-gon, he has enough accuracy to get part of the estimate. He has a lower estimate. He can say that pi ends up being bigger than 3 over 10 to the 71. And involved in that are some quite heroic square root calculations. So this really does require facility with being able to calculate square roots to quite a few decimal places. And since the Greek arithmetic was quite, let's say cumbersome, wasn't very accurate like the Babylonian arithmetic, this was quite a tour de force for Archimedes. But this is, to him, only half the story. Okay? Because what he wants to do is he wants to have an upper bound. He wants to sandwich this unknown pi between two things that he knows. Okay? So what he does is he augments this picture with another picture, which I'm now going to show you. So what he does is he takes, maybe I'll use a different color, maybe red. So he takes, let's say, the 6-gon to start off with. So just with the 6-gon, we have these 6 points here. He takes the tangents at each of these points. Let me do that a little bit accurately. So there's a tangent at that point there. And at the next point, which is this one here, there's also a tangent. Let's say that one. All right. Now these two tangents, which are adjacent, are meeting in a new point. Okay, so if you just think about this little quadrilateral here, formed from the center, the two original points in this new intersection of tangents, that's going to be a quadrilateral whose area is obviously bigger than the circular segment. And there's going to be 6 of those because we can repeat the thing 6 times around. So if he can calculate the area of this thing, he can multiply by 6, and then he has an upper bound for the area of the circle. That's his strategy. So whenever he does one of these subdivisions, then he has to augment not only the inscribed polygon, but also the circumscribed polygon. So the inscribed polygon is getting finer and finer with more and more sides, and so is the circumscribed one, and always his unknown value of pi is sandwiched between these two values. The two values are kind of getting closer and closer together like this until eventually he gets them within a reasonably narrow range. And he concludes that pi is between 3 and 10 over 71 and 3 and 1/7. So this would be like 10 over 70. That's 10 over 71, a little bit smaller. In terms of decimals, this is 3.1408 and something. This is 3.1428 and something. The real value is 3.1415, at least approximately, which is somewhere in between there. This was the best approximation for quite a while. But moreover, it set a strategy. Okay, so it set a strategy for many subsequent calculators of pi, that what we should do is we should follow Archimedes and try to estimate the circle by essentially creating kind of splines. Right? We're creating splines, polygonal splines, based on regular polygons going around the circle, either inscribing it or circumscribing it. Now let's make careful note that Archimedes was not able to obtain an analog of his parabolic area theorem. What he surely wanted to find was a relation that allowed him to reasonably easily relate the area of a circular arc, let's say this arc, A, B, C, that portion of the circle cut out by that line, and the area of, say, the maximal triangle inscribed in it, say this one, A, B, C, where this B is sort of the midpoint of the arc. That's what we have in the parabolic situation. In the parabolic situation, if this was a parabola, Archimedes would say the arc of the parabola is 4/3 the area of the circle. Wouldn't it be nice if there was some constant, like 4/3, but some different value, that worked for the circle? But he was not able to find such a thing. In fact, he was not able to find any kind of easy relationship between these two areas. Okay, and that's sort of the reality of it. The reality is that this fundamental difference between the calculation of Archimedes for the parabolic arcs and the calculation of Archimedes for the circular arcs, this separation is hugely important in the history and development of calculus and our theoretical understanding of it. Okay, so there's a gap. There's a separation that I want you to really think about. The separation between the parabolic area problem, there's a parabola, cutting off a piece, we're interested in finding the area of that parabolic piece. We can do that. Archimedes teaches us how to do that, exactly, precisely. So not only is it a question of something that we can calculate, but it's more importantly, something that we can define. We're able to define what we mean by the parabolic area. That's what Archimedes' calculation is really allowing us to do. But opposed to that, there's a big gap between this other situation with the other kind of conic sections, the circle and the hyperbola. So here's the circle and here's a hyperbola. We'll talk more about these things in a future video. So here is a piece of a circle and here's a piece of a hyperbola. And the same problem does not have a precise answer either in the circle case or in the hyperbola case. We are not able to do what we're able to do over here. All what we can do over here is get approximate values. We can get intervals. You say we can work hard and get there's an interval. The area of this segment, whatever it is somewhere inside there. And someone else can work a little bit harder and get a smaller interval and say, aha, I've got it now within a smaller interval. And then you can go away and work even more and more and more and more, and you get a smaller interval. But that's all that anybody ever can do. That's somehow the mathematical limit of what you're able to do. You're never able to actually get an exact value. Now we pretend that we can. Yes, we have this elaborate real number fantasy story involving lots of letters and such and symbolics that allow us to believe that we can get at these numbers, but the reality is that we can't. Okay? And it's important for us to look at this reality head on, not shy away from it, to really come to grips with it. So this is very important, and it's going to be a theme that runs through the calculus. Very important theme for the algebraic calculus. Now Archimedes' thinking was the forerunner of many other works in this direction. So this is a very central problem of trying to estimate the area of a circle of radius 1. And Chong Si, who lived from 429 to 501, a Chinese mathematician, used a 24,576 gon, which was 2 to the 13th, taking that hexagon and dividing it up another 12 times. And he was able to obtain this beautiful estimate. Pi is roughly 355 over 113, and that's to decimal 3.1415929. And all the way up to there, it's actually agreeing with modern calculators. So that's very impressive. Al-Kashi, almost 1,000 years later, in 1424 in Samarkand, came up with this beautiful formula for 2 pi, 6.16.59.28.01.34.51.46.14.50.01. And that may look like a very kind of funny number, but that's a number in the old Babylonian sexagesimal system. So that's with base 60. So it starts with 6, and then 16 over 60s, 59 over 60 squared, 28 over 60 cubed, etc. And it turns out, when converted to decimals, that it gives this value here, which is correct up to 6.4 there, and then it also gives these two values, but they're not in agreement with modern values. So our view is this one here, going up to the 6.4 and then 7.6. And then we might mention, amongst many other people, more modern European mathematicians who have tried to calculate pi. L. van Ceulin, or Ceulin, from the Netherlands in 1610 spent a huge amount of his life calculating pi to what turned out to be 35 decimal places. And he used a polygon also with many sides. This was 2 to the 62 sides. So it's a very fine spline, okay, with 2 to the 62 sides, and he's computing probably circumferences, and was able to get pi to 35 decimal places. That took him many, many years. Since this is such an important calculation historically and theoretically, we want to also attempt to get at the area of a circle. But we're going to have a different point of view in two different ways. First of all, we're not going to assume that there is a well-defined notion of area. And we're going to take a more applied point of view, and maybe a less ambitious point of view, and restrict ourselves to the idea of trying to get approximate areas, very much along the lines of Archimedes. So we're going to find inscribed circular splines and circumscribed circular splines, but it's going to be different from most of the historical precedences in that we're not going to look for regularly spaced ones. So we're not going to think in terms of angles and subdividing angles. Rather, we're going to think about what's called the rational parametrization of the circle. So, but before we do that, we need to become a little bit more familiar with sums and some summation issues. And we also want to say a little bit something about tangents, because we're going to need an understanding of tangents to get at the circumscribed circular splines. But we're going to come back to this problem, something that we're going to flag, and we're going to show you how to calculate the approximate area, or maybe approxarea, of a circle in a somewhat novel and maybe more efficient way than most of those historical examples that we've been talking about today. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.